Hi ho, in this video we're going to have a look at quadratic modeling instead of linear modeling. Now if you have a look at slide 1 there, you'll see that it should look pretty similar to the one that we looked at for linear modeling, to the extent that it even says linear there when it should say quadratic. It is the same kind of process, that's why I've got it there. It's just that with quadratic modeling we tend to be looking for something a little bit different. So we take a real world context, we try to apply it as a function. It might be useful to graph it, and then we use it. So when we're looking at a real world problem, we sort of try to figure out what kind of model it is. And for a quadratic model, I've got it in blue here. And as you can see, there are a whole bunch of features that are specific to quadratic modeling that you should be looking for. So for example, there's often two kinds of dimensions that it's looking for, like a length and a width, or a height and a time, or something like that. There's often a maximum or minimum that you're trying to figure out. It's called an optimization problem. So it'll say something like find the maximum height, or find the least amount of material, or something like that, which gives you an optimization, a maximum or minimum problem. And usually you should look for constraints within the problem. That is, calculations or values which will constrain the dimensions that you are needing to look for. So these are the kinds of things that will make you think, oh, I wonder if it's a quadratic model. The next thing is you have to ask yourself, what critical information do you need? You need to be able to work out intercepts or turning points or something like that so that you can get the quadratic modeling going. What do I have that fits or allows me to work out the critical information? That is a process of looking at the problem and saying, what are the facts and how do they fit? Number 4 is to then put those together to make a function. Number 5 is to sketch or graph the function, not always, but sometimes. And number 6 is to use the function to answer the problem or do some sort of analysis. So looking at slide 3 then, let's quickly zoom through that in terms of what we've got. We've got a rectangle, has a perimeter of 20 meters. Perimeter of 20 meters, it's a rectangle. Let x be the length of one side, find the maximum area. So there we go. There's that word maximum, which tells us pretty much straight away it's probably going to be some sort of quadratic. And then the next thing is to start modeling it together. It's not purely evident, I think, from the problem that this is going to be a quadratic, but once you start modeling, you'll get a sense for it. So it doesn't hurt with these sorts of problems to start with a diagram. So I'm going to draw my rectangle in, like so. And it says it has a perimeter of 20 meters. So you can see that this rectangle is going to be constrained to lengths and widths that will add up to 20 meters. Okay, that's what I mean by constraint. You've been given something in the question that allows you to say, well, that's going to constrain what I can do with my dimensions. Now, what we can do is we can either do it by hand or we can do it by sight, or we can do it by calculation, but we need to use variables to start describing the things we don't know. So for example, I can call the, I'll stick to the same language, but there are 4 lengths to a rectangle, but sometimes we call these things lengths and call the shorter sides a width, but it really doesn't matter. So we know that we've got 2 lengths x here. So if I just call these widths y, then what have we got? Then we've got another formula for the perimeter of the rectangle. It's twice the length and twice the width, so 2x plus 2y, and that is constrained by the fact that it has to be 20 meters. Now, the reason why that's useful is I can now manipulate this equation so that we've got the length in terms of, or the width in terms of x. I'll show you what I mean. I subtract 2x from both sides and I get 20 minus 2x. And I divide both sides by 2 and I get 10 minus x. So now I can replace the y with 10 minus 2x, like so. I've now got a rectangle which is purely described in terms of x, which is kind of where I want to go. Now, I said you could do this by eye rather than by calculation, and all I mean by that is have a look at that. We've got a perimeter of 20 meters. These sides are the same, these sides are the same. Oops, sorry, I've just realized I made a mistake there. I don't want to get too far before correcting that mistake. These sides are the same and these sides are the same. If the whole perimeter is 20 meters, then half of the perimeter must be 10. And so we're going to have these two sides equaling 10 meters. So if that one's x, that must be 10 minus x. So you can do it by eye sometimes as well. You can use the constraints to figure out the unknowns. Now it says find the maximum area of the rectangle. So what do we know about area? We know that area is equal to length times width, like so. But I've got an expression for y, it's 10 minus x, which I can then expand to get 10x minus x squared. Now, if you've done Maths Extended from last year, you'll know that differential calculus will help us work out this answer fairly quickly, but we don't need differential calculus in order to solve this, because if I graphed this, it would look something like this. Like so, where we'd have a 0 here, and this would be 10, okay? And so as I increase the value of x, oops, then the area will increase. But at some point, as I reach that turning point here, I'll make a maximum for the area. But then the more I make the length here, then the shorter I'll be making the width, and so the area starts shrinking again. So there's going to be a point where the area is maximized for the given length and width. Okay, so that's basically what we need to do. We need to find out the turning point. And that's pretty much what it is in optimization problems, working out the turning point so that you can say the maximum area would be this or the minimum would be this, etc. Alrighty, so the area is going to have to be turned into turning point form in order to work this out. There's other ways you can do it as well. Negative b on 2a would also work out, and probably a whole bunch of other ways as well if you think about it. If it's between 0 and 10, guess what the x value is going to be here. But anyway, let's just go for it. Minus x squared plus 10x. Oops, should change that a little bit. X squared minus 10x, because I've taken a negative outside the brackets, and there's no plus c outside of it. Now I'm going to complete the square, so I'm going to have minus x minus 5, half of 10, squared minus 5 squared, which is equal to minus x minus 5 all squared plus 25. So you can see here that I'm going to have a coordinate of the area being 25 and the width being 5. So I'll put that into the graph, 5, 25. And then I know I'm getting very messy because I'm trying to keep it to this one page. I can then conclude that maximum area is at 25 square meters. And if I wanted to, if it normally asks this, but I don't think it asks it in the question in the book, but it says what are the dimensions that give the maximum area. So the maximum area would be 25, and the dimensions would be 5, because that's what x is, and 10 minus 5, which is 5 as well. So it would be 5 by 5. Often with rectangle problems, the maximum area is when it's a square, but not always. It depends on what the constraints are. So there you go. That's basically it. Now, I deliberately chose a fairly simple one because the only way to make it harder is to make it more complicated with numbers. So be mindful that you may get more difficult problems than this, and you'll be required to use your calculator to work out specific values. And of course, if you're using your calculator, you can also get it to put it into turning point form, for example, so that you can read off the turning point quite easily. All right, that'll do for today.